Welcome back to G Fun Facts Online. Today, we are abandoning the textbooks and heading to the frozen edge of our solar system to dismantle everything you thought you knew about Uranus and Neptune. For decades, we have comfortably labeled these two worlds as the ice giants. It is a label that conjures up a very specific image: frozen, slushy worlds dominated by water, ammonia, and methane, sitting like intermediate siblings between the rocky terrestrial planets and the gas behemoths like Jupiter. This standard model has been the dogma for 40 years, built largely on the brief data we collected when Voyager 2 flew by in the late 1980s. But that understanding is currently crumbling. A massive wave of groundbreaking research from 2024 and 2025 has begun to rewrite the biography of these distant worlds. New simulations, laboratory experiments on matter at extreme pressures, and fresh analyses of old data are converging on a startling conclusion. We may have been wrong about almost everything inside them. They may not be ice giants at all. Instead, we might be looking at rock giants, or perhaps methane worlds, hiding interiors composed of exotic states of matter like black superionic ice, diamond rain, and vast oceans of mushy methane that defy our earthly imagination. To understand why the scientific community is suddenly rethinking these planets, we have to look at why the ice giant label existed in the first place. The accepted recipe for Uranus and Neptune was roughly a small, rocky core about the size of Earth, surrounded by a massive mantle of ices comprising about 2/3 of the planet's mass, all topped with a thin atmosphere of hydrogen and helium. But there is a flaw in this recipe, and it is called the carbon paradox. This is the first crack in the ice. The objects in the outer solar system, specifically the comets and planetesimals of the Kuiper Belt, are not just blocks of pure water ice. They are incredibly rich in organic refractory materials and carbon. If Uranus and Neptune formed by gobbling up these planetesimals billions of years ago, they should be packed with carbon. Yet traditional models assumed they were water-dominated. If they were truly formed from the building blocks available in that part of the solar system, the math simply does not add up. Where did all the carbon go? In 2024, researchers from the Technion Israel Institute of Technology proposed a solution that completely upends the internal map of these worlds. Their study suggests that as these planets grew, those carbon-rich planetesimals reacted chemically with the hydrogen atmosphere. This process would not just sprinkle a little methane on top. It likely created a massive, distinct layer of methane ice, potentially accounting for 10 to 20% of the planet's entire mass. Now, when we say methane ice here, do not picture the frost in your freezer. Under the crushing pressures of the deep interior, this methane would exist in a mushy state. Imagine a viscous, semi-solid lattice, something somewhere between a solid block and a thick sludge. If this model holds, Uranus and Neptune are not water worlds with a dash of gas. They are methane giants. But the rethinking does not stop at methane. While some scientists are arguing for this hydrocarbon mush, others are pushing the density dial even further. A landmark 2024 study from the University of Zurich challenged the classification by suggesting these planets might be dominated by rock. By running hundreds of thousands of random internal models and checking which ones matched the gravitational data from Voyager 2, the researchers found that models with a high rock-to-water ratio fit the data just as well, if not better, than the water-rich models. In some scenarios, Uranus could be almost entirely rock and gas, with very little water at all. This implies that Uranus and Neptune might be less like failed Jupiters and more like super-Earths on steroids, massive balls of silicate rock wrapped in a thick hydrogen blanket. This reclassification blurs the line between the giant planets and the terrestrial ones, suggesting a continuum of planetary formation that we are only just beginning to understand. Now, let us peel back the clouds and descend into these worlds. If we could go deep into the mantles, we would not find a simple ocean. We would descend into a realm of physics that exists nowhere on Earth, where the rules of chemistry are twisted by millions of atmospheres of pressure. Deep in the mantles, where the ice layer was supposed to be, scientists now believe there lies a phase of matter known as superionic water. On Earth, water is liquid, solid, or gas. But at pressures exceeding 2 million atmospheres and temperatures of several thousand degrees, conditions found about 1/3 of the way into Uranus or Neptune, water molecules break apart. The oxygen atoms freeze into a rigid, crystal lattice, becoming a solid, while the hydrogen nuclei, the protons, flow through this lattice like a liquid. This material is a hybrid. It is simultaneously a solid and a liquid. It is electrically conductive, like a metal. And perhaps most strikingly, it is black. If you could see a block of superionic water, it would look like a piece of hot black coal. The existence of superionic water is no longer just a theory. In recent years, laser experiments at facilities like the Lawrence Livermore National Laboratory have created this material for fractions of a second, confirming that water really does enter this bizarre state at ice giant pressures. But if black ice isn't strange enough for you, let's talk about the precipitation. For years, diamond rain was considered a fringe theory, But now it is becoming a central pillar of our understanding of these worlds. The process begins in those carbon-rich layers, the methane mush we discussed earlier. As pressure increases, methane molecules are squeezed until they break. The hydrogen escapes, and the carbon atoms are forced together. Under extreme pressure, carbon's most stable form is diamond. These are not microscopic gems. Models suggest they could grow to the size of hailstones or even boulders. Because diamonds are denser than the surrounding hydrocarbon fluid, they sink. Imagine a slow-motion rain of glittering diamonds falling through a thick, hot, black sky of hydrocarbons, descending for thousands of kilometers. As they sink deeper, the temperature rises. Eventually, even diamond cannot remain solid. They may melt into a layer of liquid carbon. Recent simulations suggest that near the core, there might be a sea of liquid carbon with chunks of solid diamond floating in it, literal diamond bergs, drifting on a metallic ocean. This process releases gravitational potential energy through friction, which is converted into heat. This diamond heat might explain why Neptune radiates so much more energy than it receives from the Sun, while Uranus is much colder. This brings us to the mystery of the two siblings. One of the biggest questions about the ice giants is why they look so different. Neptune is active, with high-speed winds and dark storms. Uranus is pale, calm, and eerily cold. A 2025 study, led by researchers at UC Berkeley, provides a compelling answer called phase separation. We tend to think of planetary interiors as well-mixed smoothies, but at these pressures, water and hydrogen-carbon mixtures might become immiscible, like oil and vinegar. The study suggests that inside Uranus, these fluids have separated into distinct layers. Uranus may have a stable, stratified interior where a clean water layer sits distinct from a hydrocarbon layer. This stratification inhibits convection. Heat from the core cannot bubble up to the surface because the layers do not mix. The heat is trapped inside, leaving the surface cold and the atmosphere calm. Neptune, on the other hand, may have not fully separated yet, or has a different composition that allows for more convection, letting internal heat escape to drive the ferocious storms we observe. This new internal model also solves the long-standing magnetic mystery. The Voyager 2 flyby left scientists baffled by the magnetic fields of these planets. Unlike Earth or Jupiter, whose fields are aligned with their rotation, the ice giants' fields are a mess. They are offset from the center by huge distances and tilted at wild angles, 60 degrees in the case of Uranus. For decades, we thought maybe we just caught them during a pole reversal. But the new Beyond Ice models explain this perfectly. If the interior is not a fluid ball of iron, but a stratified layer of superionic water and mushy methane, the magnetic field isn't generated in the deep core. Instead, it is generated in a thin conductive shell of fluid much closer to the surface. Because the dynamo is generated in this shallow shell, the resulting magnetic field is unstable, lopsided, and chaotic. We are seeing the signature of a complex, layered interior projected into space as a twisted magnetic cage. So why does any of this matter? Rethinking Uranus and Neptune is not just about solving a local puzzle. It is about understanding the universe. When we hunt for exoplanets orbiting other stars, the most common type of planet we find is not a gas giant or an Earth twin. It is a planet about 2 to 4 times the size of Earth, a mini Neptune. Because we do not have a mini Neptune in our solar system, Uranus and Neptune are the closest analogs we have. If we misunderstand them, we misunderstand the majority of planets in the galaxy. If Uranus is a rock giant, then many of the mini Neptunes we see might be habitable super-Earths with thick atmospheres, rather than uninhabitable gas balls. Fortunately, we are not leaving this to guesswork forever. The scientific community has officially prioritized a return. The National Academy's Decadal Survey ranked a mission to Uranus as the highest priority new flagship mission for NASA. The proposed Uranus Orbiter and Probe, or UOP, is designed specifically to test these new theories. It will launch in the early 2030s, arriving in the 2040s. The orbiter will map the gravitational fields to X-ray the interior, looking for the methane mush and the separate shells of rock. Crucially, a probe will detach and plunge into the atmosphere to measure the noble gases, the fingerprints of formation. Until then, we must adjust our mental image. We used to think of Uranus and Neptune as the boring planets, static balls of frozen water. We were wrong. The Beyond Ice revolution has transformed them into the solar system's most exotic laboratories. They are likely worlds where oceans of black, hot ice swirl beneath clouds of green methane, where the sky rains diamonds into a liquid carbon sea, and where the magnetic fields are tangled knots of energy. By moving beyond the simple ice giant label, we are finally beginning to see these worlds for what they likely are: complex, stratified, and dynamic bodies that bridge the gap between rock and gas, holding the secrets to the formation of our solar system and the thousands of planetary systems beyond. That is all for this deep dive. Thanks for listening to G Fun Facts Online.